Alright, given some +2 nanocoulomb charge out there in space that we'll put at the origin of our coordinate system, makes math easy. What would be the electric field? Now realize electric field equation states that you need K Q per R squared. So we need to do some math here. So recall that R as a vector is the observation location minus the source location. Alright, so since our source location in this case is the origin, okay, so that's just going to be 0, 0, 0. And that means it's going to be a relatively simple calculation. And the magnitude, well, our value will just be the negative 0.2 in all three components, which means that the magnitude of this vector is just going to be the square root of the sum of all the squares. And this will work out to be 0.35 meters. Now, our electric field, if we're looking for a vector form of this, well, then we're going to need to find our unit vector, which will be relatively simple given the fact that we just found the magnitude of our vector. And so plugging and chugging those numbers leads to a unit vector that points in a bunch of negative directions, all of them. It's a negative field here, so to speak. And now we can apply all of this information and actually get the electric field. So K Q per R squared, and we'll put our unit vector in there. So 9 times 10 to the 9th Newton meter squared per Coulomb squared is our Coulomb constant. Our 2 nanocoulombs of charge, our separation distance squared, and the R hat that we just figured here. And so when you plug in Chugsville, all of that, you get a minus 84 in all three directions, newtons per coulomb.